Hey all you cool cats and kittens, Mr. Nortillo here from Big Pre-Calculus Rescue, going into the notes for 9-6. This first problem is not a new problem, it's an old problem, just converting this equation into the standard form equation for a circle. We've reviewed this already. Let's go right down to problem number 2. Converting this equation into the standard form for an ellipse. Now, we learned about this standard form equation for an ellipse in the previous lesson, where the denominator of the x squared term is the radius of the ellipse in the x direction squared, and then the denominator under the y squared term is the radius of the ellipse in the y direction. Either denominator might be bigger than the other, depends on whether the ellipse is wider than it is tall, in which case that x squared denominator would be bigger, or maybe the ellipse is taller than it is wide, and then that denominator would be bigger. Anyway, let's get right to the process. It's much the same as with circles. You group the x's and the y's together, but the first key difference comes right here, where you need to factor this coefficient out of your x terms before you try to do that completing the square part by filling in that missing term. You need to factor that coefficient out. So we factor the 25 out and we get x squared minus 2x. Then you take half of that negative 2. So if you take half of that negative 50 and square it and fill in a number there, you're already off on the wrong foot, and I don't think there's any way you're going to get that corrected. Got to factor the 25 out first. Take half of that negative 2, which is negative 1, which, by the way, is what shows up on the next line of work, x minus 1. That's no accident. That's always the way it should be. You square that minus 1, and you get plus 1. And then here's the other difference between doing this work for an ellipse as opposed to a circle. Writing down plus 1 does not mean we have added only 1 to the left side of this equation. We've added 1 times 25. So we have to add 25 to the right side of this equation. And then the same business occurs with the y terms. You've got to factor this 9 out. You'll get y squared plus 6y, because 54 divided by 9 is 6. Take half of that positive 6y, which is a plus 3, that's what shows up down there. Square that plus 3, you get plus 9. But again, we haven't just added 9 to the left side of the equation. By writing down plus 9, we have in effect added 9 times that 9. So we have added 81. So we add 81 to the right side. Now add all these terms up, of course, you get 225. Change each of these trinomials into the square of a binomial. And again, where does that minus 1 and that plus 3 come from? They come from half of that minus 2 and half of that plus 6. Always. Again, no accident. Okay? So we turn these trinomials into the squares of binomials. We add all these together, we get 225. Last step, and this is different from circles also, we want the right side of that equation to be equal to 1. So we divide by whatever number that is. We divide everything in the equation by that 225. Now, if you do the arithmetic right, if you do the process right and the arithmetic right, you will be able to reduce these numbers to 1 over some nice whole number, 1 over 9. 9 over 225 reduces to 1 over 25. I'm just making that commitment to you and that promise to you that that's the way it's going to be for any problems you get from me in this course. I mean, it doesn't have to turn out that way mathematically, but it will for any problems you get from me. And I'm letting you know that so that in case you get to this last step and you're trying to reduce these numbers and it does not reduce to 1 over something, that should be a red flag for you, that you've made a mistake somewhere in the process. Okay? So now, from this standard form equation of the ellipse, We can tell exactly where the center of the ellipse is. It's at +1, -3. We can tell what the radius in the x direction is. It's 3 units. The radius in the y direction is 5 units. We could draw a really good picture of this ellipse if we wanted to, now that it's in standard form. Okay. Next problem, very much the same. About the only thing different in this example is we have a positive 352 here. So we need to subtract 352 from both sides of this equation. We start out with a negative here, right? Up here we had a negative 119, so we needed to add 119 to both sides of the equation. Okay. But then again, we group the x's, we group the y's, we factor the 4 out, and we get x squared plus 4x. Take half of that plus 4, that's a +2. Square that +2, and you get +4. So that's the new term that we're writing down. But by writing down +4, we are in effect adding 4 times 4, which is why we add 16 to this side. When you factor the 16 out of these terms, you get y squared minus 10y. Take half of that negative 10y, which is -5. Actually, just half of the negative 10, which is -5. Square that -5, you still get a positive, right? Whether you square a positive or a negative term, you're going to get a positive result. And by writing down +25, we have in effect added 25 times 16. I would expect you to pull out your calculator for that, of course. 25 times 16 is 400. So we've got to add 400 to the right. Add all these terms together, you get 64. Turn these trinomials into the squares of binomials, and then divide everything by 64. And again, these numbers, 4 over 64, should reduce to 1 over something. They do, 1 over 16. And these numbers should reduce to 1 over something, and they do, 1 over 4. So we're done here. Now, one last little thing before we look at the next example. Some people get it in their heads that the denominators in these terms, 9 and 25, will just be, they think, they can predict that these denominators will just be what the coefficients of the x squared and y squared terms were to start out with. And in this case, that's true, right? We had a 25 in front of the x squared. We end up with a 25 denominator under the y squared term. We had a 9 in front of the y squared. We end up with a 9 underneath the x squared term. And in this example, that also turns out to be the case. But in the next example, it will not turn out that way. And truly, there's no way to predict in advance whether those coefficients will end up being the denominators of the fractional terms or not. You just have to do the work. And so here is the work of that third problem. Again, group the x's, group the y's. Oh, here's another thing that's a little different about this one. There is no y to the first term, right? Okay, there's no y to the first term. Let's keep going. We added 8 to both sides. We got to factor this 8 out. Factoring the 8 out of the 48 leaves a 6. Half of the 6 is a 3. Square the 3, you get 9. 9 times the 8 is 72, so we add 72 to the right. If there is no y to the first term here, then there's no completing the square. There's no finding a third term for the trinomial when there isn't even a second term to begin with. So you just leave this alone. Okay? Same would be true if there was not an x to the first term. You wouldn't have to find a third term when there is no second term. So just leave that alone. Okay? Add these terms together, you get 80. Now divide everything by 80. Divide by 80, divide by 80, divide by 80. This reduces to 1 over 10. This reduces to 1 over 16. Okay, so this is what I was saying. 10 and 16 are not the original coefficients. Okay? Now, they happen to be multiples of the original coefficients. 16 is 8 times 2. 10 is 5 times 2. But again, there really isn't any way that we could have predicted that. I mean, these numbers could have turned out to be 3 times those numbers, 4 times those numbers. It really just depends on the value of this coefficient. That's all. I mean, if I had made this coefficient a positive 32 instead of a negative 8, then these denominators would have turned out to be 8 and 5. But if I had made this coefficient a negative 48, then these denominators would have turned out to be 15 and 24. So there's just, as I said, there's just no way for you to predict what these denominators are going to be. Don't skip the work and just think you know what the denominators are going to be. Do the work, okay? And then here was a new kind of question on this lesson here. And these questions get, you get 3 choices eventually after we learn about hyperbolas. The question is, which of these equations represent circles and which represent ellipses? And the key is, of course, the coefficients of the squared terms. The coefficient there is a 1. That coefficient is a 3. When the coefficients of the squared terms are different, you're going to get an ellipse. Because if the coefficients of the squared terms are different, when you rearrange that equation into standard form equation, then the denominators are going to be different from each other. I mean, if we rearrange this into standard form, we might not get denominators of 1 and 3, but we absolutely will get denominators that are different from each other, which means you're going to have different radii in the x and y directions. And so there's no way it could be a circle. So in this case, the coefficients are the same, 1 and 1, so it's a circle. And in this case, the coefficients are the same. It doesn't matter that they're not 1. Some people will see this and go, oh, when the coefficients are 1, then it's a circle, but they're not 1, so it's not a circle. That would be incorrect. Okay? The coefficients can be something other than 1 and still be a circle. The question is, are they the same or are they not the same? And they are the same, so it's a circle. Again, think about the denominators if we converted this equation into standard form. If we're starting out with a 5 in front of the x squared and a 5 in front of the y squared, then when we divide everything by whatever this number turns out to be, then the denominators are going to end up being the same. And so you'll have the same radius in the x direction as you do in the y direction. And that means it's going to be a circle. Okay? So that's this lesson, 9-6. The next video we'll have a lesson for 9-7, and that will be it for this week. Take care.